All right, today's lesson we're going to talk about continuity. So you've heard this word before. You've heard the word continuous. You've heard that word in relation to functions, which is what we're going to be looking at. So the definition we've used in previous classes, or at least the one I used to use when I taught Algebra 2 and Pre-Cal, was a continuous function is a function you can draw the entire thing without picking your pencil up off the paper. Okay, so we're going to put a little bit more formality to the definition of continuity today, and we're going to use limits to do that. Okay, so a function f is said to be continuous at x equals c, if and only if. Okay, so what we're actually looking at for this definition is continuity at a specific point on the graph. Okay, so three things have to be true for a function to be continuous at a specific point. Number one, the function evaluated at that point has to be defined. So if you're looking at a graph, a way to think about this is there has to be a closed circle there. Okay, so if your function has like an asymptote where c is located, or if it has a hole in the graph where c is located, then your function is not continuous at that point. All right, second part, the limit as x approaches c of f of x exists. So you have to have a limit that exists. Okay, so I'm going to write a little more formal. How do we know a limit exists? We know the limit as x approaches c from the left of f of x has to equal the limit as x approaches c from the right of f of x. So you need to make sure the left-hand and right-hand limits agree, and then you know the limit exists. All right, if either of those things are false, then your function is not continuous at that point. But if both of those are true, then you check the third thing. The limit as x approaches c of f of x has to equal f of c. Okay, so that third part, for number two to be true, the limit could be approaching an open circle. It could be approaching a hole. So the limit would still exist, but there's a hole in the graph. So the only way for a function to be continuous is if the limit is approaching the closed circle. So it can't be approaching an open circle. It has to be approaching a closed circle value on the function. All right, so we are going to sketch a few functions here that break the rules so you can see what some discontinuities might look like. All right, so letter A says f of c is not defined. There's actually a couple ways we can draw this one out. So I'm going to draw a little squiggle, and we'll do an x, y axis over here, and we'll do another one over here. Okay, so I'm going to label c on my x-axis. So one way the f of c could be not defined is it could be an asymptote, vertical asymptote there. All right, and then your graph, let me put a horizontal asymptote in here. Graphs don't have to have a horizontal asymptote. I just think it looks a little nicer if we have that there, so that's why I'm putting it. All right, so your graph might go like this and then like this. Okay, so f of c is not defined, therefore the function, which is in blue, is not continuous, and you could see that I was not able to draw the whole graph without picking my pencil up. I had to draw that, pick my pencil up, and then draw this part. Okay, the other way would be if c, right here, is a hole in the graph like that. Okay, so I'd have to draw my function going there, and then I have to pick my pencil up to go on the other side of the hole and keep drawing my function from there. All right, so that's two ways for the function for f of c to not be defined, which causes our function to be discontinuous at that point c. All right, letter B, the limit does not exist. So there are a couple different ways to do this, but the most common way that we will see is when the left-hand limit and the right-hand limit do not agree. They're not the same. So what this would look like in function form, we have our c is we'll have like a point right here. I'll make that a closed circle, and then another one up here. Can't be both closed circles, but I could have switched those and it wouldn't have mattered. All right, and then so the left side of my function could be going to this closed circle here, and then the right side of my function coming from the open circle like that. So the limit approaches different values for the left and the right, so the limit does not exist. All right, what if both of these are true, but the third rule is broken? So the limit does not equal. So this is going to be very similar to this graph right here. Our graph will have to have a hole in it. Okay, so we have C, we have a hole, And then I have my function, which is going through that hole. Okay, but this says that f of c is defined, and the graph I just drew, f of c is not defined. So for f of c to be defined, but the limit doesn't equal f of c, that means f of c is some other closed circle point like that. So the function goes through the hole, but there is a defined point. So f of c is defined, check. The limit exists, approaches the same value from the left and the right, check. But they are not equal to each other. That's why this is discontinuous. All right, lastly, the continuous one. So this is where your limit approaches the closed circle value. Okay, so I have f of c, it's defined with a closed circle somewhere, and my function approaches that closed circle from the left and from the right. And I could have drawn this without picking my pencil up off my paper because I am going through that hole right there, like that. All right, there are 3 types of discontinuities. You need to know all 3 of these. You need to be able to recognize them on the graph, and you need to be able to show from the definition why the discontinuity happens. So this is called a point discontinuity. I'm just going to draw a picture. Point discontinuities are holes. Okay, so it could be like that, or it could be like this. Okay, so from the definition, this could be one of 2 things. It could be f of c is not defined, or it could be the third one, that the limit as x approaches c of f of x does not equal f of c. Sorry, I wrote f of c in there. I meant to write f of x. So let me erase that right there. All right, limit as x approaches c of f of x does not equal f of c. So it's going to be one of those two options there. All right, second one is a jump discontinuity. So just like it sounds, the graph jumps from one section to another. So this is where you might have a graph going to like an open circle like that, and then maybe the closed circle is in another location like that. So this one is pretty much exclusively going to be the limit as x approaches c from the left of f of x does not equal the limit as x approaches c from the right of f of x. And what that means is the limit does not exist. So that breaks our second rule. All right, and the third type is an asymptotic discontinuity. So we have some sort of asymptote at x equals c. I'll draw this one without a horizontal asymptote. So we can kind of come from down here up like that, and then from here down like that, maybe. This one might have like a slant asymptote in there. Okay, and so this one is going to pretty much exclusively be f of c is not defined. Because if there's an asymptote there, then the c is certainly not defined. I suppose we've seen some weird graphs where like you can draw a piecewise function. They put like a closed circle on the asymptote, but that's very strange. Okay, it's possible, but I wouldn't worry about that weird example. Okay, so those are your 3 types. You need to be able to recognize them on the graph and then be able to describe using the definition that we just did up here why they are not continuous. Okay, a point discontinuity is also called a removable discontinuity, and that's because you can redefine the function in such a way to make the function continuous there. Okay, jump discontinuities and asymptotic discontinuities are non-removable because the functions which contain them cannot be redefined at a point. Okay, so all I would have to do, like if this was my point discontinuity, is I would have to take this point and just move it right there and fill that circle in, and now I would have a continuous function. Okay, so we can do that pretty easily with a piecewise function. But if I wanted to try to do the same thing with a jump discontinuity, I wouldn't simply be able to just move this point up right there. I would have to move the next point up, and the next point up, and the next point up, and now I'm redefining the entire side of this function. All right, we're not allowed to do that. So jumps don't. And then for asymptote, I would have to somehow redefine this where the asymptote goes away completely. All right, and that's not something we're going to be allowed to do. Okay, so the only one that we call removable is a point discontinuity because all I have to do is move one single point and into a spot, and then I would have a continuous function. Okay, this one down here talks about endpoints. So you can be continuous at an endpoint. But since you can't do a left-hand limit and a right-hand limit to make them agree, you only do a one-sided limit. So we do the limit as x approaches a from the right for the left endpoint, or the limit as x approaches b from the left. So I'm going to describe this using this example. I think it's a little easier to understand. So you should recognize this from our pre-cal review. This is a semicircle. Okay, so let's draw our semicircle. It's centered at 0, 0, and it has a radius of 5. We have endpoints at 5 and negative 5. Go up like this and like that. Okay, so what we're saying is that this function is continuous at negative 5 and it's continuous at positive 5. So it is continuous on the closed interval. See the equal signs from negative 5, less than or equal to x, less than or equal to 5. Okay, so how do we prove continuity using our definition up here? Okay, well, f of 5, well, I'll do negative 5 first. F of negative 5 exists. There's a closed circle there. And then we just do the limit as x approaches negative 5 from the right. So you can only come from the right like that. And that limit is equal to 0, which is equal to f of negative 5. Both things are equal to each other. Therefore, the function is continuous at that endpoint. Okay, and on the other endpoint, f of 5 exists. It's a closed circle. We know it's equal to 0. And then if we do the limit from the left side, the limit as x approaches 5 from the left, it approaches that closed circle right there. So the limit is equal to the value of the function, which means that it is continuous at that point. All right, so we are going to do a few examples here where we find the values of x at which the given function is discontinuous. We're going to identify that discontinuity as one of the 3 types. Then if it's removable, we will describe it as removable or not removable. And if it is removable, we are going to redefine the function in such a way to make it not removable. That isn't written here, but we're going to do that anyway. And then we'll sketch a graph. All right, so with anything, any graph that we have to do with rational functions, especially, good idea to factor. So let's factor x plus 2, x minus 2, divided by x minus 2. I'm going to be able to cancel my x minus 2's. And so I'm left with x plus 2. Even though I canceled it, if your problem starts with a denominator and there's a number that you can plug in to make the denominator 0, that is a discontinuity, no matter what. Now, if we can cancel out, it changes what type of discontinuity it is, but it's still a discontinuity every time. Okay, so our answer for number 1, find the values of x. This is discontinuous at x equals 2. So if I plug in 2, my denominator would be 0. Can't ever have a denominator be 0, even if that denominator gets crossed out. All right, since we crossed it out, you should remember that that causes a hole in the graph. And a hole is a point discontinuity. A point discontinuity is the only type that is removable. So since it's removable, we are going to redefine the function. F of x is equal to, so it's going to be equal to x plus 2 at every point. Let me write the word if x is not equal to positive 2. So it's going to be equal to this function, this reduced form, everywhere except for this one point. It's not going to be equal to there, because if I plug that into the original, I would get 0 over 0. All right, so we are going to have another piece down here if x is equal to 2. Okay, let's do the graph first, and we'll come back and fill that part in. All right, so all we're doing is graphing a linear function here. So I have a y-intercept at positive 2. Okay, I know x equals 2 is going to be an important point, but before I get there, I can just do my slope 1 over 1. So rise to 3 over 1. All right, and this is where it happens. So I'm going to go rise over run again, but that's going to be my hole in the graph. Okay, I'm going to go down and left a couple times to get my x-intercept, and I think that's good enough. All right, so to redefine the function, to make it continuous, all we have to do is fill in that hole right there like that. So if I were to fill in that hole, what would my y value have to be at x equals 2? Well, 2, 4. is the point. So we can redefine when x is equal to 2, we're going to say our function is equal to 4. That fills in the hole, which makes our function a continuous function, because now I can draw the whole thing without picking my pencil up off the paper. All right, next one, we have a denominator. This time the denominator cannot be canceled out. So just like the last one though, anytime you have a denominator, whatever number you could plug in to get 0, that is a discontinuity. So that is our answer to number 1 is x equals 3. Number 2, if you cannot cross the denominator out, that denominator, that discontinuity makes an asymptote. So this is asymptotic discontinuity. And asymptotic discontinuities are non-removable. So we will not be able to redefine our function like a piecewise. You can only do that for the removable discontinuities. All right, so to create our graph here, we have an asymptote at x equals 3, a vertical asymptote at x equals 3. This function is bottom heavy, so we have a horizontal asymptote at y equals 0 on the x-axis. To get a point to plot somewhere, I just plug in 0 for x and I get negative 1/3. So that's down here somewhere. And I can draw my graph in through that point like this. And then this function has no togetherness. So my other curve will have to go in the top right like that. All right, this next one is our signum function. Okay, so again, this has a denominator. So this has a discontinuity at x equals 3. Okay, the type, though, a little confusing. Like, are we allowed to cross these out to make a whole? Not exactly. Are we not allowed to cross it out? So it's an asymptote? Again, no, not really. So let's do the graph over here first, and then we'll come back and fill in the rest. So 1, 2, 3, there's x equals 3. Okay, and if I plug in, let's do a couple more over here, 4, 5. So if I plug in 4, I get 4 minus 3, which is 1, over 4 minus 3, which is 1. 1 divided by 1. So that's 1. 4, 1, right there. And so if I plug in 5, 5 minus 3 is 2, and 5 minus 3 is 2. 2 divided by 2 is 1. Okay, so hopefully you remember what this looks like. We have an open circle at 3 because we can't be equal to 3, and then every value to the right is equal to positive 1. Okay, and then if we go left, so if I plug in 2, I get 2 minus 3, which is negative 1. Absolute value makes it positive 1. 2 minus 3 is negative 1. So 1 divided by negative 1 is negative 1. So 2, negative 1. And if I plug in 1, 1 minus 3 is negative 2. Absolute value makes it positive 2. 1 minus 3 is negative 2, so positive 2 divided by negative 2 is negative 1. And so we get an open circle at 3, and then it goes to the left at negative 1, a horizontal line at negative 1 going to the left. Okay, so you can see we do have a discontinuity, but it is that third type we haven't discussed yet in our examples. This is a jump discontinuity. And jump discontinuities are non-removable. So we will not be able to redefine our function as a piecewise function, and we're done with that one. All right, so over here on this one, piecewise functions are always very popular with discontinuity problems because they can easily be written to produce a discontinuity of some sort, and they can be multiple different types. You could have an asymptote in there somewhere. You could have a jump, or you can have a hole. Okay, so you just have to kind of pay attention and to what type it is. So what I do want to point out, though, is if this wasn't piecewise, if all they did was give us x plus 2, then that would mean that f of x equals x plus 2 is a linear function. That's always continuous, that function by itself. This function is also a linear function. So that function is always continuous by itself. So the only location where a discontinuity could occur would be at x equals 1. Okay, and I can tell you just from looking at the equation, I know that this is going to be a discontinuity at x equals 1. Remember the first rule of continuity? I'm going to flip back. F of c is defined. Do you see an equal sign on either one of these? So f of c, if I plug in 1, isn't defined because I'm not going to be able to plug it into either spot. Okay, now it might not be a point discontinuity. It might be another type. Okay, but I know that x equals 1 is going to be a discontinuity because f of c is not defined. All right, now before we do the other one, similar to the last problem, let's go ahead and graph this and see what it looks like, and then we can make our decisions about the rest. Okay, so x plus 2, if I plug in 1, 1 plus 2 is 3. So 1, 3, and that's an open circle because it's not equal to. And then I graph to the left, less than 1. So slope is 1, so we just go down 1, left 1, and that's my y-intercept. And I'm going to do that a couple more times to get my x-intercept right here at -2. All right, there's that graph. All right, this one, if I plug in 1, 2 minus 1 is 1. So that's going to be an open circle. And then I have a slope of -1. So I'm going to go down 1, right 1, like that. All right, so looking at this, f of c is not defined, but I wouldn't call this a point discontinuity. They would have to be connected to each other. This is, again, a jump discontinuity. And jump discontinuities are non-removable. All right, next one. This is a quadratic function. Quadratic functions, there's no denominator. And that's really denominators and jumps. So denominators and piecewise functions, or this function in particular, are really the only types we see with discontinuities. So this is continuous everywhere. Okay, so we can draw a quick graph of this. This is the parent function shifted up 1 unit. If I plug in 1, I get 2. If I plug in -1, I also get 2. So draw your parabola shape through those, and we're done. Okay, I can draw the whole thing without picking my pencil up off the paper, like that. All right, last one. Maybe give this one a try on your own before, pause the video, try it on your own, then you can unpause and see how you did. Okay, so what you should have done first is factor. You get x on top, and down here you can factor out an x, leaving you with x minus 3. Okay, the x on top and the x you just factored out can cancel, which leaves you with 1 over x minus 3. Okay, we actually already graphed this right up here. However, it's going to be a little different because we do have that x here. Okay, so we actually will get 2 discontinuities this time. Okay, so discontinuity number 1 is going to come from that x we crossed out. It's going to be x equals 0. Okay, that discontinuity, since I crossed it out, is a hole. That is a point discontinuity. Point discontinuities are removable, which means I should be able to write my function redefined as a piecewise function where I fill in that hole. Okay, I'm going to wait on that part. We'll do that after we graph. Okay, but there is a second set of discontinuity. It's not set, but a second point of discontinuity, and that's at our other factor on our denominator at x equals 3. Now that one did not get crossed out. So when it doesn't cross out, that's going to be an asymptote. So it's asymptotic, and asymptotic is non-removable. All right, so we will not be able to write a second piecewise function to redefine this one. We will only be able to redefine the point discontinuity. Okay, so a lot of the graph is going to start the same way. We have a vertical asymptote at x equals 3. Okay, it's bottom heavy, so we have a horizontal asymptote at y equals 0. All right, if I plug in 0, I get -1/3, but x equals 0 is the hole in the graph. So make sure that you make that an open circle when you graph it this time. Now my curve will still go through that point right there. And it still doesn't have any togetherness, so my other curve will go up here. All right, so if we write our piecewise function where we redefine this, and all I'm doing with the piecewise function is I'm filling in this hole right here. Okay, so the regular function will be this 1 over x minus 3, the simplified form. And that's true if x is not equal to 0. Okay, remember we're trying to fill in the x equals 0. So our second piece is going to be when x does equal 0. What does my y value have to be to fill in that hole? Okay, well, when I plugged in 0, I got negative 1/3. So negative 1/3 would fill in that hole. So that redefines the function as continuous at that point. Now, it still has a 1 discontinuity at x minus 3, but if we redefine it this way, this function right here, let me underline it in a different color. This function right here is now the exact same as this function right here. See how we have that point right there, closed circle at 0, negative 1/3? Okay, so that's what we did. We were able to redefine this function as a continuous function at x equals 0. All right, that'll do it for continuity. Hope you enjoyed that one. I'll see you on the next video.